Today we are going to explore the paper entitled "A Lightweight MapReduce Framework for Secure Processing with SGX." This paper has been published in 17th International Symposium on Cluster, Cloud, and Gate Computing, and I am Saeed Mufrad, the presenter. First, let's see the outline of the paper. So this paper explains MapReduce as a typical tools for big data analytics. Then paper proposed a lightweight, secure MapReduce framework which leverages Intel SGX. So the use of Intel SGX is for providing confidentiality guarantees for MapReduce operation, and it wants to be an alternative to a previous cryptographic approaches. Then paper evaluates its framework by using the K-means clustering algorithm. So first we need to know what the MapReduce framework is. MapReduce framework is proposed by Google in 2008. The generic model of MapReduce, which composed of the map and reduce function, is used to implement applications that can leverage parallel task processing. In the generic model, the input data is located over a series of mapper nodes which apply in parallel a map function responsible for mapping individual data items to a finite set of predefined keys. Then we have the shuffle process, which in this process, the output of the mapper nodes will be sent to the reducer nodes. So in reducer nodes, a reduce function executes in parallel, which process each set of data corresponding to the certain key. So MapReduce has many use cases. Some simple use cases is for processing tasks such as counting, sorting, and searching data, and also very complex tasks and algorithms such as cross correlation and page ranking. Uh, Basically, Google uses MapReduce framework for its web crawler and for providing web page ranking. So, because MapReduce works with big data, so it needs lots of computational resources, and in order to save cost acquiring the large parallel computing resources, MapReduce currently uses public cloud. So the issue is public cloud implementation of MapReduce lacks security, and it is not suitable for sensitive applications. And some research has been done to provide security to the MapReduce framework. So we will learn about those technologies. We have two main approach for securing MapReduce jobs. The first one is leveraging complex cryptographic techniques for protecting the confidentiality of the data being processed in the map and reduce functions. For example, proposed solutions was using homomorphic or partial homomorphic applications, but we have several issues when we use these techniques. The first issue is the choice of the encryption is determined, mostly determined by the task to be executed in the reducers. Therefore, a limitation is that the customized data encryption scheme should be used, and often that customized encryption scheme have limited expressiveness and are applicable to only a small class of application. We cannot apply the cryptography to all uh, set of applications. The second issue is cryptographic solutions incur high performance overhead because of the complexity of encryption schemes. And the last one, an important one, is cryptographic techniques just addresses the confidentiality of the data being processed, but not the integrity of the code itself at the runtime. So the second solution is using hardware-assisted trusted execution environment, or TEEs, such as Intel SGX. So basically, TEE provides an isolated space for executing code where confidentiality and integrity of code and data can be guaranteed. For example, Intel Software Guard Extensions, or SGX, is considered the powerful TEE, which has introduced in the Intel's commodity processors, starting with the Skylake generation CPU family in late 2015. So SGX executes code privately in a secure space, which is called enclave, and the CPU, the hardware, takes care of the confidentiality and integrity of the code and data at the runtime. For the system architecture tech stack, authors propose a self-contained framework for securing MapReduce, which leverages the Intel SGX. Their system architecture combines a lightweight virtual machine based on the Lua language, which can be executed inside the SGX. Also, they added a MapReduce library inside the SGX, and also they use a publish and subscribe service for communication between the client and worker nodes. So, authors claim that this solution is independent of the particular characteristics of the map and reduce functions. So this solution can be considered as a general solution and can be used for any map reduce problem. So author claimed a specific code which needs to be executed in MapReduce service can be integrated as a simple script, Lua language script, which can privately run in isolation in the SGX, where data is decrypted only inside the enclave. So it provides the integrity and confidentiality of the data and code. And also, authors claim that the basic word count MapReduce job can be implemented in this framework with less than 30 lines of code, or LOC. In the architecture paper, uses the publish and subscribe, or pub/sub communication model. Let's see what it is. It is one of the most effective ways of distributing information in a distributed system. So in the generic model of pub/sub, we have publisher nodes and subscriber nodes. Publisher nodes submit data to a pub/sub routing service and as a publication, which is formed of a header describing the data and a payload containing the effective data. The pub subrouting service then matches the publication's header with the subscriptions registered by the subscriber nodes, and then routes the matching publications towards their destinations. In this paper, author used an available secure content-based routing SCBR implementation that implements the pub/sub communication model inside the SGX. So in the brief, in the SCBR, the matching and routing of publications is determined inside the SGX enclave provided by the pub/sub service, which is typically this service deployed in a public cloud. All subscriptions and publication messages are encrypted and they use the symmetric cipher while they are outside of the secure enclave. So the subscriptions and publication headers are decrypted inside the enclave where subscriptions are stored in this secure model. Then the service routes the publication payloads to to matching subscription. This is how SCBR is working, and this paper use this secure version of publisher and subscription communication model. Architecture uses the secure content-based routing PubSub implementation to a MapReduce service by designing the PubSub communication protocol between nodes involved in this process. So we have two different type of nodes, worker nodes and client nodes. Worker nodes can play and can have two different roles. They can be subscribers and publishers. When they are working in the subscribers role, they register queries that announce that they want to be hired by MapReduce job opening. They register themselves to the system. And when they work as a publisher, they submit the desired job details, such as they are willing to work as a mapper or reducer, and also they publish the result of work that they have done. For client, we have different roles. When client works as a subscriber, client registers itself to the system, and also when the client works as a publisher, it publishes the job opening. So they say I have a job which I need to be executed in this system. Then also client coordinates the routing messages from mapper to reducers. So which means the client delivers the code and data to the registered, the hired workers from the system, and also the client obtains the results from the hired worker nodes. This paper has used k-means for its evaluation. Let's see how k-means is exactly. So k-means is an unsupervised learning algorithm which widely used in data classification applications. So the flow of k-means is as follows. In step one, the specific number of k's of cluster is selected. And based on that k value, k corresponding centers are defined in the model, which means we define randomly k value to be the centers of those clusters. In step two, data items are iterated and assigned to the nearest cluster center through calculating the Euclidean distance between the data items and the center for those of all k value we have. In step 3, every cluster center again is recomputed as the centroid of the assigned data items, which means the average of those points which is associated in the clusters, the mean of those values will be a new center of that cluster. And in next step, step 2 and 3 repeat until the termination criteria is reached. The termination criteria can be the sum of the distance between the old and the most recent cluster center is below a given threshold. For another criteria can be the new cluster doesn't change based on the previous cluster, and also the value of the cluster increases, which means the convergence start to expanding. So at that moment, k-means break the iteration loop. For implementing the k-means in the MapReduce model, step 2 is put in the map function, and step 3 is put in the reduce function, as displayed here in this figure. As you can see, we have data. In this paper, they use two-dimensional data points. So they split data directly to the map function, and in map function, mappers compute the distance to each data point for each cluster center and assign point to the cluster center. And in the reduce node, it computes the new cluster sentence and send it to the client program for the monitoring the results, and the client program computes the error and decide whether to continue the iteration or breaks the loop. Here in figure 2 displays the entities composing the solution architecture. So we have client router or secure content-based pub sub engine, and we have workers which can be in mapper and reducer nodes, and we can see workers and mapper and reducer nodes, and the router, they are executed inside the enclave. So also we have the clients. Clients provide the code to be executed, the data to be processed, and gets the result back from the system. So the SCB R engine is responsible for securely store the subscriptions which contain the condition under which each message should be forwarded to the corresponding entity, such as client, mapper, reducer. Subscriptions always stored inside the SGX protected memory, and every matches processing is done inside the enclave. When data goes out for communication, everything is always encrypted in this system. So in this slide, we have session establishment protocol, and it shows when the system is started up, what exactly happens in the system. So in the sequence diagram, as you can see, worker nodes first register the availability for MapReduce job opening to job opening subscriptions. After that, client registers themselves the detail of the map and reduce task through the job detail subscription. At this time, client advertises its jobs through the job opening publication, which is received by workers that previously registered as available in this system. So the workers submit their desired details regarding the job to a job details publication and sending in the message payload for the subscription if they are willing to work as a to receive the code and data for the particular role they want to do, to be a mapper or reducer. At the end of this negotiation, if client decides to hire a worker, it registers on the SCBR router, communication router, the received subscriptions for code and data on behalf of the worker. So when client do this, the client established by doing this, actually client established the MapReduce chain and keep tracks of how many workers the client it has hired, and and what role each worker has, whether they are mapper or reducer. So the figure 3 shows this sequence diagram. This slide shows the provisioning of code and data in this framework. In figure 4, we have the sequence diagram of provisioning of code and data. So as you can see, client published the map code type and client published the reduce code type. And also client includes the number of reducers aligned with the Lua script for map code type and the number of mappers for reduce code type. So the purpose is to make the worker aware of how many message signaling the end of the stream they should wait before considering the work done and even starts a job. It is important. The reason is the reduce phase can only start when all data arrived to the intended worker. So also the number of reducer received by a mapper is important because it is used in a hash function in the map code type that takes as argument the map key and that reducer numbers, and returns the which reducer, the reducer ID that data, the result has to be forwarded. So the client, after sending the code, splits the data between the mappers, and it uses the destination ID, includes including that in the map data type publication, so that each data is reached to the intended map worker. Then map workers decrypts the received code and store it inside the enclave, and they wait to start the job. When all data arrive, mapper performs the process, and each of the results will be forwarded to the intended and proper reducer. So in order to get the reducer ID, mappers use that provided key and the number of reducers as the arguments to the hash function inside that map code type code, and they can calculate the reducer ID by that. So as we can see here, the shuffling phase also is conducted by the mappers in this framework. They don't use the another module for doing a shuffle. So in this system, in order to send the data to the next step, each worker uses a specific function in Lua script, which is called push function. When they call that push function, they pass the key and value to the SCBR router, and after that, the SCBR router takes care of the communication aspects of that data, and it makes sure that data will be received by the intended entity in the framework. So in this slide, we have the testbed. For the testbed, they use two SGX capable machine, both with processor Intel i7-6700 and 8 megabyte cache memory, and 4 physical core, which is capable to take care of 8 threads logically. And the total memory installed, the RAM was 8 gigabytes. And for the storage, they use the SSD of 256 gigabytes. So for the encryption, all messages encrypted with the AES counter mode, which use the 128 bits for a key and input vector, and everything, all messages are encrypted outside of the enclave, and only they are decrypted inside of the enclave. For the process placement, they put the client, which is responsible for providing code and data to other entities in machine 1, and also machine 1 runs 8 mappers and 5 reducer. For machine 2, they defined 8 mapper and 5 reducers. So they used 8 mappers because they wanted to use the full power of parallelism in their machine, which had the 8 logical core. And the number of reducers was set to be a divisor of input data size to be a similar and to provide the even distribution of work among all data input. For the experiment, authors partitioned and randomly generated bidimensional coordinates into K clusters, and in the map step, they assigned each observation to the nearest center by computing and comparing the distance, and the reducer step updates the center to become the centroid of assigned coordinates. The process repeats until the average distance between the most recent calculated centroid and the one from the previous iteration is less than a threshold. So this is the approach they use to measure the k-means performance in their framework. Table 1 shows the memory section size of executable and shared library that are loaded into enclaves. As we can see here, there are few, the size is not big and it is few bytes, which is good because one of the goal in the task execution environment is to making the trusted computer base or TCB as less as possible. So the few kilobytes of bytes of data is a good job. Figure 5 illustrates 4 out of 76 iterations that came in troops to converge when the threshold was set to 0. In this example, they generated 100,000 observations and points, and the k value was defined as 10. As we can see in the first frame, the initial centroids all set on the bottom left, which means they limited the domain of generated coordinates for k. So every initial cluster happens here. And they claim that it quickly, after 6 um, iteration, starts to uh, find the positions that are closer to the best fit. And as we can see, after 19 iterations, we have 10 points and some clusters. And the best fit happened in uh, 76 iterations, and the algorithm finished. This is the result for 76th iteration and the last iteration of the clustering. In this slide, figure 7 shows the average time it took to complete one iteration of k-means with different input size, which means they wanted to see the effect of number of k and number of points and observation data. So as we can see, when the number of k increases, the number of the time for calculation increases slightly, but it can be noted the big difference happened when the number of observation data is increased. For example, when the number of observation data is 1 million, so the time to calculate it is increased. And the effect of the number of k is less than the number of observation in this algorithm. This slide shows the encryption overhead because this application uses IntelliSGX. Everything is encrypted and decrypted. So it is the bottleneck, one of the bottleneck in the trusted execution environment. In this work, encryption overhead was obtained by comparing the average time it took to complete one iteration with and without encryption, both inside and outside the enclave, and then they calculate the average of these two values and reported that. So the average encryption overhead, average SGX overhead. So as we can see, when data point increases to the million now, so SGX in average imposed more than 200%, more than 2x slowdown to the original work, and this is a relative valid slowdown we can expect from the SGX machine. And it is about 2x slower just for the encryption. This slide shows table 2, which is data volume exchanged per iteration. So as we can see, when the number of observation data is 1,000, the amount is less, a few kilobytes. When it is 10,000, it's getting reaches the megabytes, and when it is 100,000, it's about still in the megabytes. And for the 1 million, the observation and data points, we have about 100 megabytes of data transfer just for the shuffle. So, in conclusion, this paper proposed a lightweight framework for implementing secure MapReduce application in an untrusted environment such as public cloud, which are capable of using SGX machine. And paper leverage SGX enclaves and try to use the trusted execution environment to fix the complication and limitation of prior secure MapReduce solutions such as cryptography solutions such as homomorphic and partial homomorphic MapReduce um, approaches. So for the limitation, I identified paper did not provide any mechanism for monitoring the whole job execution and integrity, and I assume this as its weakness. So if there is no way to understand if the final result is accurate, and I think they're going to address this in the future work.